Everyone. In today's video, we are going to talk about stereochemistry for substitution reactions. And the stereochemistry is going to be different depending on whether you have an SN1 reaction or an SN2 reaction. So we're going to focus on SN1 first. And let's draw a reaction here. So let's say that we have the following. Okay, and that's going to react with a chloride ion. So remember from earlier we talked about electrophiles and nucleophiles. So which one of these reactants would be the nucleophile? The chloride ion, right? Because remember, nucleophiles have lone pairs that they can donate. Or another way to think about it is they're attracted to anything that's positively charged or partially positively charged. So the chloride ion is our nucleophile. Now our other reactant is the electrophile. And we'll see why in a bit. Okay, so remember in an SN1 reaction, we have a first order reaction, and there are two steps in an SN1 reaction. In the first step, the leaving group leaves. And I know that the iodine is our leaving group because remember, it's a really large atom, which means it can accommodate a negative charge really well and still be stable. So the iodine atom will leave, and we'll end up with a positively charged carbon. And that carbon is now bonded to only 3 different groups. So it's going to be trigonal planar. So I'm drawing that carbon now as if it's in a trigonal planar geometry, but I'm still showing a wedge and a dash to indicate that even though the methyl and ethyl groups that are attached are in the same plane, one is going away from us and one is coming out towards us. Okay, so then the iodide ion will still be kind of hanging out nearby. And then we have our chloride ion. Now remember, when we have a carbocation, the reason that the carbon is positively charged is because we have an empty p orbital. So let's draw our p orbital above and below the plane of this molecule. All right, so now remember in step 2 of this reaction, the nucleophile is going to attack the carbocation, or the positively charged carbon. Now, there are 2 different ways that the chloride ion here could attack. It could attack from the top or from the bottom. And this is going to give us 2 different products with different stereochemistry. Okay, so let's draw the 2 possible products here. Let's see, I'm going to draw, top, bottom. So if chloride attacks from the top, that's going to push the methyl and ethyl groups downward. Because remember, in VSEPR theory, electron groups want to be as far apart from each other as possible. So that carbon is going to gain a 4th group, which means it's going to adopt a tetrahedral conformation. Okay, so if chlorine attaches from the top, again, that will push the methyl and ethyl group down. But methyl will still be coming out towards us, and ethyl will still be pointing away from us. Okay, and then what if the chloride ion attacks from the bottom? Now, if chloride comes in from underneath, that's going to push the methyl and ethyl groups up. So the methyl group is still pointing out towards us. The ethyl group is still pointing away from us. Okay, so one thing that I notice is that we do have a stereocenter. So where is that stereocenter in each of our products? So it's on the carbon that is now bonded to chlorine. Okay, and the other carbon is not a stereocenter, so you might be tempted to say that that carbon is a stereocenter, but it's bonded to two methyl groups, so that disqualifies it because remember, a stereocenter is bonded to four different groups. All right, so let's assign R or S to each of these stereocenters. So let's start with the product on the left. Would that be R or S? And you can pause the video if you want to try that on your own. All right, so looking at this, if we prioritize our groups, chlorine would have priority 1, and then we have 3 different carbons we have to consider. We have this carbon in the ethyl group, the carbon on the end of the methyl group there, and then this carbon over here on the right. So which one would have greater priority? Well, the carbon on the right is bonded to 2 other carbons, whereas the carbon in the ethyl group is only bonded to 1 other carbon, and the carbon in the methyl group is bonded to 3 hydrogens. So the carbon on the right will have second priority. And then looking at the ethyl carbon versus the methyl carbon, which one would have third priority? The ethyl group. And then the methyl group will have fourth priority. Okay, so if we draw a circle going from 1 to 2 to 3, it looks like it's going towards the right. So that would tell me it's an R configuration, except our lowest priority group, the methyl group, is pointing out towards us. So that means it's actually an S configuration. So most of the time we see hydrogen as the lowest priority group, but other groups can also be the lowest priority group. And in this case, methyl is the lowest priority group. But the same rule applies. If your lowest priority group is pointing towards you, then you flip your assignment. All right, so let's try the other one. So the other product, would that be R or S? And if you want to try it on your own first, you can pause the video. Okay, so we have the same priorities that we did before. This time our circle is going in the opposite direction. So it looks like it's going towards the left in a counterclockwise direction. So that would be S, except our lowest priority group is pointing towards us. So this would be R. So what we have is a pair of enantiomers. So when SN1 reactions occur, you end up with a mixture of stereoisomers. And sometimes you'll have enantiomers, but you could also have diastereomers depending on how many stereocenters are in your molecule. So for instance, we might have had another stereocenter on the right-hand side, and that would have stayed the same. But the carbon we're attacking would have different assignments. So you could end up with diastereomers as well. So let's just write that down, that SN1 reactions result in a mixture of stereoisomers. So that could be enantiomers or diastereomers. Now, I also wanted to go over a couple of terms for these types of products. So if chlorine attacks from the top, you'll notice that it's attacking from the opposite side of where iodine was. So the nucleophile is attacking opposite where the leaving group was. And so we would call this product the inversion product. So the nucleophile attacked from the opposite side. And again, that's just relative to where the leaving group was. But if chloride attacks from the bottom, then it's attacking from the same side that the iodide ion is, or where the iodine atom was. So we would call this the retention product. So the nucleophile attacked from the same side. Okay, but notice this iodide ion is still kind of hanging out near the carbon atom. It hasn't gone away quite yet. And that's normal in a reaction. So when the chloride ion comes in from the top, it doesn't have anything competing with it. There's nothing there blocking its path, right? But when it attacks from the bottom, we have this iodide ion just kind of hanging out there after it left, and that's going to prevent the chloride ion from attacking. So if chloride attacks from the bottom, this is more difficult due to the leaving group hanging out, let's say. So the leaving group is still kind of hanging around, and the chloride ion can't quite get in there. So it's almost like on a soap opera, someone's ex is hanging out, still hanging around, and so the new love interest can't quite, pair up with who they want. However you want to think about it. So when we form these two different products, it's much easier to form the inversion product. Okay, so in an SN1 reaction, the inversion product is slightly preferred because it's easier for the chlorine to attack from the top. So there's a slight preference for the inversion. Let's say product. Okay. Oops, sorry, didn't mean to go to the next slide quite yet. All right, so again, when you have an SN1 reaction, you actually end up with a mixture of products, and they're going to be a mixture of stereoisomers, and remember that could be enantiomers or diastereomers, and that's because the nucleophile is going to attack the intermediate carbocation either from the top or the bottom, but the top or the opposite side, so that could also be the bottom depending on how you're looking at it. So if the nucleophile attacks from the opposite side of the leaving group, that's going to be easier. So that's the preferred product, but you still get the other product too, the retention product. Okay, so let's look at SN2. So remember, SN2 is different from SN1. It's still a substitution reaction, but it's a second order reaction, and there's only one step. So let's look at a reaction. Oops. Let's call it reaction A. And let's say we have a carbon bonded to bromine, hydrogen, which is coming out towards us, methyl going away from us, and in the plane we have ethyl. And then let's just draw a generic nucleophile. It doesn't have to be a specific nucleophile for this example. And then let's draw the same thing down below, but we're going to call this reaction B. Okay, so there are two possibilities here. So we already know the nucleophile is going to attack the electrophile, and the nucleophile is going to attack the carbon that's bonded to bromine, because bromine is electronegative, so it's going to pull electrons away from carbon, making carbon partially positively charged, and we can even draw that just as a reminder. And then remember, in an SN2 reaction, the nucleophile attacks and the leaving group leaves all in one step. So the nucleophile could attack from the front, and then the leaving group will leave. Or the nucleophile could attack from behind, and then the leaving group will leave. So we have two possibilities here. Now the way we can determine which one is preferred is by drawing the transition state. So let's draw the transition state for example A. And remember, in a transition state, you have bonds breaking and forming at the same time. So let's draw our carbon with its bonds. That will stay the same. And then we'll show that its bond to bromine is breaking and its bond to the nucleophile is forming. And to indicate that you have a transition state, we normally put brackets around the transition state and we label it with this little symbol up here. Okay, now remember, during this step, we haven't fully broken our bond to bromine, but bromine is partially negatively charged. And the nucleophile is starting to form its bond to carbon, so it's no longer negatively charged, it's partially negatively charged. Now, let's draw the transition state for example B. So again, we'll draw our carbon, but this time I'm going to draw the hydrogen and methyl group kind of pointing up more, and you'll see why in a second. So the nucleophile is going to start forming a bond from behind, and bromine is starting to leave on the opposite side. And that's why I drew my bonds kind of pointing straight up and down on this one, because for a brief moment, carbon will be, it will have a configuration where the 3 bonds in the middle are trigonal planar. So let's draw brackets around our transition state, and we'll draw that little symbol for the transition state. Oh, my pen decided to be bold. There we go. So again, during this process, bromine is still partially negatively charged, and the nucleophile is also partially negatively charged. So now, comparing those two transition states, which one do you think is more stable? The first transition state, where the nucleophile and bromine are on the same side of the molecule, or the transition state where the nucleophile and the bromine, or the leaving group, are on opposite sides? So, remember, according to Vesper theory, electron groups want to be as far apart from each other as possible. So which transition state is more stable if we think about Vesper theory? The second one, in example B, right? So the two partially negatively charged groups are opposite each other and they have more room. Whereas in example A, the nucleophile and the leaving group, which are both partially negatively charged, are kind of in each other's space, and they don't like that. So example B has a more stable transition state. And remember, that is coming from Vesper theory. So electron groups want to be as far apart as possible. Now, let's draw the types of products we would get from each reaction. So in reaction A, the nucleophile is attacking from the front. So we have, oops, my pen isn't working. There we go. So we would retain that same configuration that we had before. So this would be called the retention product. And of course, bromine is hanging out, so we can draw the bromide ion down below. And then in the other reaction, reaction B, the nucleophile attacks from behind. So that's going to push the hydrogen, the methyl, and the ethyl group in the opposite direction from where they started. So this will be called the inversion product. And again, bromine's hanging out somewhere. We'll just draw it up here, I guess. Okay, so we already said that in example B, the transition state is more stable. And for an SN2 reaction, that's really important. So SN2 reactions only produce inversion products. So that transition state is really important. We want a stable transition state. Okay. So again, with SN2 reactions, the nucleophile could have maybe attacked from the front, but it's just not favorable. So the nucleophile actually attacks from the back. And we refer to this as backside attack, and you end up with the inversion product. All right, now on Canvas, under under study guides in modules, I posted this worksheet, and it's really just a worksheet that you can use as we move through these lecture slides, or you can use it as a study guide and see if you can remember all of the different characteristics of an SN2 reaction versus an SN1 reaction. So let's just kind of go through and summarize what we know so far about SN2 reactions versus SN1 reactions. So the mechanism. Well, we know that SN2 happens in one step. So we would actually call that a concerted reaction. And in that one step, we know that the nucleophile attacks and the leaving group leaves. And then we know that an SN1 reaction is different because it's a stepwise reaction. So there are multiple steps. And in the first step, so the rate limiting step, the leaving group leaves. And that's all that happens in the first step. So then we also saw that we can write a rate equation for each of these reactions. So an SN2 reaction, remember, is a second order reaction. And the rate is equal to a rate constant times the concentration of the substrate. And remember, the substrate is the electrophile. And then we'll multiply that by the concentration of the nucleophile. So again, for SN2 reactions, the rate really depends on both the nucleophile and the substrate. But in an SN1 reaction, because the rate limiting step only involves the leaving group leaving, the rate is just equal to the rate constant times the substrate concentration. All right, and then we just talked about stereochemistry, and we said that for an SN2 reaction, we'll only produce the inversion product. But for an SN1 reaction, we're going to end up with both a retention product and an inversion product, but there's some preference for the inversion product. Let's see, we'll write preference for inversion. And then in the last lecture video, we talked about the role of the electrophile in SN2 and SN1. And if you remember, in an SN1 reaction, we have an intermediate, that's a carbocation. And the carbocation, if it's tertiary, will be really stable. But if it's, for instance, a primary carbocation, that will be less stable. So for electrophiles under SN1, we can write that tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than methyl carbocations. And remember, the carbocation stability depends on hyperconjugation. So we'll also write that down. Carbocation, oop, I misspelled that. Carbocation stability. Okay. Now, SN2, on the other hand, is the opposite, because remember, the nucleophile attacks at the same time that the leaving group leaves. So we want the electrophile, or the substrate, to be less bulky in order for the nucleophile to attack easily. So we're actually going to flip our order here. So a methyl substrate would be better than a primary substrate, then a secondary, then a tertiary. So if you have a tertiary substrate, it's going to prefer an SN1 reaction over an SN2 reaction because the nucleophile can't really attack a tertiary substrate very easily. And again, that's due to what we call steric hindrance. Or you could also write bulkiness. Okay, so this is what we've learned so far about SN1 and SN2 reactions. And as you can see, we have a few more things that we need to go over. So we'll also go over the role of the nucleophile. We'll go over the role of the leaving group. And then finally, we'll talk about preferred solvents for each of these types of reactions. So I will see you in the next video.